In the last two classes, we discussed about the generic push relabel algorithms, and we also have proved that the algorithm is correct in the sense that if it terminates with max flow as the value it computes. Today we are going to see a new version of push relabel algorithms known as relabel to front algorithm. What we learned about the algorithm for finding max flow using the generic push relabel method. Such algorithms find maximum flow by applying the basic operations push and relabel. We know that the generic algorithm keeps on applying one of these operations until none of them are enabled in a residual network. And such algorithms allow to apply push and relabel operations in any order. It is not demanding what is the next vertex, intermediate vertex at which we need to apply the push operation or relabel operation. And the complexity of the basic or generic push relabel based algorithm is not to be upper bounded by the square of the number of vertices multiplied by the number of edges. Not that in a dense network where large number of edges are there, edges can be in the order of number of square of the number of vertices. If there are n vertices, then n into n minus 1 by 2 edges are possible. It is possible to get an algorithm which is asymptotically as faster as this algorithm and better for dense network, that is when the network is fully connected, all the edges are there, then this is going to be the number of vertices raised to 4, because this is going to become, in the worst case, the number of square of the number of vertices. So it is the number of vertices to the power 4 in the worst case for a dense network. And we are going to see relabel to front algorithm which works better for dense networks. And the idea is to carefully choose the order of push and relabel operations and manage the network data structure efficiently. So how will you store the network data structure or represent the network data structure? Find an efficient representation using a nice data structure and carefully choose the order in which you are going to apply push or relabel. And relabel to front algorithm carefully selects the order of these operations to get a complexity of order of n cube if n is the number of vertices. So it is cubic in the number of vertices. See that for a generic algorithm, this is the complexity, and for a dense network, if all the edges are there, this could be the number of vertices to the power 4, but this is only to the power 3. So that is why it claims that for a dense network, when there are large number of or all possible edges, then a relabel to front algorithm can perform better. Now, before we see what that algorithm is, or some lemmas that we need to look at the algorithm, before that let us see what is the basic idea behind that algorithm, how it works. It maintains a linked list of vertices to be processed. You know that whenever there are overflowing intermediate vertices, we have to discharge them or send that excess flow to the neighboring vertices. That is what a push relabel based algorithm do. And so maintain that intermediate vertices as a linked list, and each vertex u in the linked list is processed one at a time. It will take one vertex which is an intermediate vertex with an excess flow, then that excess flow will be completely discharged before selecting the next one. And here processing means discharging the excess flow at that vertex, and discharging means pushing or relabeling. If u is a vertex with some excess flow, if push is enabled, then push will be used to discharge, or relabel will be done at that vertex so that it will get a possible edge through which you can discharge. And why the name relabel to friend? When this algorithm relabels a vertex u, relabels means increasing the height of u, then it moves that vertex to the front of the linked list, and that is why the name relabel to friend. And the algorithm is going to depend on admissible network, which is defined in terms of what are called admissible edges. They are nothing but edges through which a push operation is enabled, that is it. Formally, if G a flow network with the source S and sink T, and F be a pre-flow, not that in push relabel based algorithm we relax the flow conservation property, and hence the flow is what is called a pre-flow, and H be a height function on the vertex head. And I hope you remember these basic terms from the previous two lectures. Then we say that the edge UV is admissible if the capacity of that edge is greater than 0 and the height of u is 1 more than height of v. That is, push is enabled, that is it. When push is enabled on that edge, this is the precondition of on push, and the capacity should be greater than 0. So, this is exactly the precondition of push operation. So, if push is enabled on that edge, then it is called admissible. If it is not enabled, it is called inadmissible. We can see an example. Given a residual network like this, and all these green edges are admissible and red edges are inadmissible. Example, if you look at Vx, the height of V is 1, which is 1 more than the height of x. And if you look at a red edge, this is inadmissible because their heights are same, push is not enabled. And now in terms of admissible edges, you can define admissible network. It is nothing but the network where only the admissible edges are present. So simple. If you only consider admissible edges, the network that you are getting is called admissible network. And the relabel to friend algorithm needs to maintain what is called admissible network, because it is only going to make use of admissible edges. Now, before we see the algorithm, we can look at two lemmas. Lemma 1, let G be a flow network with the source S and sink T. Let F be a preflow on that network and H be a height function. Then the lemma claims that if a vertex U is overflowing, that is some excess flow is there, and UV is an admissible edge, meaning from U to V you can push, then it claims that push is enabled on that edge, and it also claims that when you do that push operation, it will not create any new admissible edges. That means you don't have to change the residual network to proceed with, because you are only interested in admissible edges. If the lemma is correct, it says if you do a push operation, then you will not introduce any admissible edges. Not only that, it may cause the same edge to become inadmissible. We can prove it, and the proof of the first condition is very easy, because it follows from the definition of admissible edges. An edge is called admissible if and only if a push operation is enabled on that. So, this is a trivial property, follows directly from the definition of admissible edges. And for proving the second one, it claims that it will not create, a push operation will not create a new admissible edge. Not that if you push from U to V, the only edge you are adding is the reverse edge to permit sending back the flow or flow cancellation. Okay, and because you are pushing from U to V, as a precondition you know that the height of U must be 1 more than the height of V. And if you rewrite, you will get the height of V as 1 less than the height of U, just taking it to the other side. Hence, if you add that edge, VU must not be admissible, because for this to be admissible, the edge VU to be admissible, you have to satisfy this condition. If you want to push a flow from V to U, the height of V must be 1 more than the height of U is what you need. Then only the edge VU is said to be admissible. But here we got that it is the other way. Height of V is not 1 more than, it is actually 1 less than height of U. So, even if you add the reverse edge, it is not going to be admissible. So, we proved. So, what we proved is that if U is an overflowing vertex with an admissible edge outgoing from U, then push is enabled on that edge for sure, and when you do that push operation, you will not introduce any more admissible edges. So, you do not have to change your network, admissible network. That is the point here. When we later look at the algorithm, we can see that when the algorithm is doing a push operation, it is not modifying the admissible network. It is not required as per this lemma. Lemma 2, given the same network and a pre-flow and height function, it claims that if U is an overflowing vertex and there is no admissible edges going out of U, that is U is overflowing, but no outgoing edge from U, then it claims that relabel U is enabled. Also, relabel is enabled, and if you perform that, after that at least one edge leaving the vertex U must be an admissible edge. That is, you are getting one admissible edge after relabeling so that you can push. And also it claims that there cannot be an admissible edge coming to you. Going out of you, you will be getting one, and you will not have a reverse case, that is an edge coming to you which is admissible. We have to prove it, and proof of condition 1 is simple because we know it from lemma 3 of the previous lecture, where we proved that if U is an overflowing vertex, then the lemma 3 in the previous lecture proved that push UV is enabled or relabel U is enabled. That is guaranteed. Either the push is enabled on U or relabel is enabled. And here we have this condition, no admissible edges leaving U, means push is not enabled. And therefore, from this we know that relabel must be enabled, and so the first condition is proved. Second one, it follows immediately from the definition of the relabel operation that what is relabel? You will get a height which is 1 more than the minimum height adjacent vertex. So there must be a vertex after relabeling such that the edge is admissible, because you are getting height of U as 1 more than height of B. So height of U is equal to 1 plus height of B, which is exactly what you need for admissible edge. Now the second part we have to prove, there is no admissible edge coming to U. Now suppose that there exists a vertex V such that from that vertex V an edge is coming to U and which is admissible after the operation. We have to prove that it is not possible. And if it is admissible, this must be true by definition of admissible edges. If there is an edge from B to U, height of V must be 1 more than height of U. Not that we just performed a relabel operation, that is, after increasing the height of U plus 1 is only the height of V. So previously the height of V must be strictly greater than this quantity, because after you increase the height of U plus 1 is same as height of B. So before increasing, this quantity should be strictly more. This is what I am telling. And so it is a contradiction, because we know that for any edge in the residual network, if you want to have an edge from V to U, what you need is height of V is less than or equal to height of U plus 1. And this is a basic property of the height function, and that is what we discussed in the first slide of the previous lecture. So we are getting that contradiction, and hence we proved that if U is an overflowing vertex and there is no admissible edges leaving U, then relabel must be enabled on that vertex. Also, after relabeling, you will definitely get an admissible edge leaving U, so you can discharge. Also, you will not get or you will not have any admissible edge coming back to you, meaning no need to process that vertex again. Once you pick that vertex for discharging, discharge it completely. So lemma 2 gives you a proof that no need to look at the same vertex again because of the second property. No admissible edge can come to it. Now we can discuss the data structures used in that algorithm. Edges in the relabel to front algorithm are organized into neighbor list. We can see what are neighbor lists. Given a flow network, the neighbor list is a linked list for a vertex u is represented as u dot n. The neighbor list of the vertex u is a singly linked list containing the neighbors of the vertex u. Example, if you look at the vertex x, then the x dot neighbor linked list is this. And what are the elements in it? A vertex v is called a neighbor if there is an edge going from u to v or coming from v to u. If an edge is there in either direction, then it is a neighbor. For example, for x, s is a neighbor because this edge is there, u is a neighbor because this edge is there, v is a neighbor because the reverse edge is there, and y is also a neighbor because x to y edge is there. So, if there is an edge going from v to u or going from u to v, whatever direction, then u and v are neighbors. And it does not matter in what order you linked them together. And the header node or the first node in the list is pointed to by the head field of the neighbor list. The neighbor list is h dot n, and that has got some fields. One is the head pointing to the first node in the list, and the next pointer is named as next neighbor, s dot next neighbor. The field is now pointing to the next neighbor. And for each vertex u, there is another field or attribute current, u dot current points to the vertex currently under consideration in this list. And to start with, the current will be pointed to the same node as head is pointing to. Or to start with, the current will be u dot current, that is the current neighbor is what it is called. And to start with, it is initialized to the first node in the linked list representing the neighbors. I hope you are getting it. Now let us proceed. There is something called neighbor list. An overflowing vertex u can be discharged by pushing and relabeling. You know that discharging means do push and relabel operations to completely discharge or push the excess flow at that vertex. And this is the discharge procedure which will be used from the relabel to front algorithm. And what is this? We want to discharge u, means if there is an excess flow, that is what it is taking, then the excess flow needs to be completely discharged. And what is it doing? It takes the next neighbor from that list and then it checks whether the next neighbor is nil or not. Nil means no neighbor is there. That means no admissible edge, and hence from the previous lemma 2, a relabel must be enabled, and you perform that relabel. Then from the same lemma 2, we know that after the relabel operation, at least one edge must be admissible. So whenever you perform relabel, the current will be modified as the head of the neighbor list of u. Okay, again you are checking from the head what is the admissible edge, right? Whether you want to see one of the adjacent vertices to which the edge is admissible. Okay, so you are starting again from the first neighbor. Okay, first I mean the header node in that neighbor list. Okay, so if there is no neighbor, relabel will be performed. If there is a neighbor and it is admissible, the edge is admissible means push operation is enabled and there is a capacity greater than 0. Then what you do? You just push. And note that these operations cannot add admissible edges, that we proved, and that is why such a statement is not there. So if a neighbor is not there, relabel it. If a neighbor is there and it is admissible, the edge to that neighbor is admissible, then you push. Otherwise, what you do? Oh, that neighbor is not going to help you. That a neighbor is there, but the neighbor is not having an admissible edge going to it. Then what you do? You pick the next neighbor and repeat. So, note that the algorithm will definitely empty the excess flow at u once it is called. So, that is the discharging procedure. Now, we can look at the relabel to front algorithm. And what is it doing? First, it initializes the preflow, the same sub procedure called from the basic push relabel algorithms. So, same initialization, I hope you remember it. And after that, we need to make a linked list of overflowing vertices. We do not know which are the overflowing intermediate vertices, and not that the algorithm will perform a discharge only if it is overflowing. So, what is it doing is it takes all the intermediate vertices into the linked list, because it does not know which all are overflowing, but that is fine. And after that, it makes the current node of every node in that linked list as the first node in the neighbor list of that. Okay. Then it is trying to discharge by picking nodes from this linked list. It is always it is first taking it from the first position, that is the first node is taken as u, and until there exists some node in that list, what is it doing? It just copies that height, because if a relabel is performed, the height will be increased. This is just remembering it temporarily to see whether relabel is performed or not. Okay, that is the only purpose. So, what it basically do is it picks vertex u from the linked list, then it performs the discharge, the previous procedure. And after discharging, it checks whether the discharge relabeled that vertex or not. If it is relabeled, that vertex, wherever it is moved to the front of this linked list, and that is why the algorithm is known as relabel to front. Whenever you relabel, the vertex is coming to the front. Okay, and after that, you are taking, once you discharge u, no need to consider that again, because that is what we proved from the lemma. Then what is it doing? It picks the next intermediate vertex from that list and it continues. So, it will go for all the intermediate vertices, that is n minus 2, and then it will finish. And you can prove that discharge will take order of n square, which is where n is the number of vertices, and hence this algorithm is taking a worst case time of n cube. order of n cube, where n is the number of vertices in the given flow network. So with this we are finishing this lecture, and today we looked at relabel to front algorithm, which is an improvisation of the basic push relabel method, in which the overflowing vertices are maintained as a linked list, and it carefully selects the next not to be discharged, and getting an order of n cube algorithm, where n is the number of vertices in the given flow network. So with this we are finishing the topic flow network, and we will be starting the next topic in the next lecture. Thank you.